All right, so we are picking up here with our Chapter R material, and this is part 2 of the videos covering Chapter R. We're going to get into exponent rules here, and when we talk about exponent rules, I always kind of compare it to like a game. If you think of a game, you have all of these different moves and tools you're allowed to use, and I think of exponent rules as the moves and tools we are allowed to use in simplifying exponential expressions. So I think if you can think about it that way, it's a little less daunting and maybe a little bit more creative. So here we have, if we are multiplying two terms that have the same base, their exponents are added together. So for example, if I had x to the 5th power times x to the 8th power, that would be x to the 13th power. If we have expression to some power and then to another power, those get multiplied. So these two are often confused here. So if I have, let's say, x to the 5th power and then that being cubed, that would be x to the 15th power, 5 times 3. Now, division works very similarly. We can subtract those exponents. Let's say if I had x to the 10th power over x to the 3rd power, 10 minus 3 is 7. What I oftentimes recommend to students, because sometimes the exponent on bottom will be bigger, is I recommend actually writing it out. So x to the 10th is literally 10 x's. And then x to the 3rd is 3. And then you're just canceling out 3 x's, and we're left with 7 of them on top. So that's another tool you can use. Now this is everybody's favorite because it's super easy. Anything, doesn't matter what your base is, it could be 1,000,000 to the 0 power is equal to 1. So I could have 1.738 to the 0 power, that's equal to 1. I could have x to the 0 power, that's equal to 1. Now here we're getting into negative exponents, and what you want to remember with negative exponents is that they move and become positive. So negative exponents move down to the bottom and become a positive exponent. If you have a negative exponent in the denominator, it's going to move to the top and become positive. So negative exponents move and become positive. For example, if I had, let's say, y to the negative 3 power, that would become 1 over y to the 3rd. Or if I had 1 over a to the negative 2nd power, that would become a squared up top. Here we can see that powers can be distributed. So if I have a times b inside parentheses, that power is distributed onto both of them. So if I have, let's say, 3xy squared, let's actually make that x to the 4th power. Then this square becomes or gets distributed onto all 3 of these terms. So 3 squared would become 9, x to the 4th to the 2nd power, so that would be this rule, a power to another power, that gets multiplied, x to the 8th, and then y squared. And the same is true with division. It can be distributed over both as long as the parentheses are covering both the top and the bottom. So this would be x to the 4th power over 3 to the 4th power is 81, and then y to the 4th. Okay. So let's apply these to some problems here. In this first example, we have this times this. There's no exponents on them, on the outsides of these or anything, and we can reorder this in any order I want. If you think about it, 1 times 2 times 3 times 4 is the same thing as 2 times 3 times 1 times 4. I can reorder those in any order I want, but the product is still the same. I can do the same thing here. So I can multiply negative 2 times negative 3 times a squared. So you can see I'm grouping things by their like term. B to the 4th times b to the 4th. Well, negative 2 times negative 3 is 6. A times a squared is a to the 3rd power, and b to the 4th and b to the 4th is b to the 8th. In this next example, now we have a fraction, and right away I see this easy one here. We know m to the 0 power is just 1. Now there's no exponent out here, but I can do some reducing here. 18 and 27 have a common factor of 9. 18 divided by 9 is 2. 27 divided by 9 is 3. I'm realizing this pen is not the easiest for you to see, so let me go over that in a different color. All right, so 2 and 3. And then I have some negative exponents. So this m to the negative third power is going to move to the bottom. So I've done kind of a lot of work there already. So we've got a negative 2. That 18 reduced and became a 2. This m to the negative third power is going to move to the bottom and become positive. So I took care of that. Got an n to the fifth power on the top, n to the fourth power on bottom, and I've got a 3 on bottom. And there's still some simplifying I can do here. I have 4 n's on bottom and 5 on top, so 4 of those will cancel out, and I'm only left with 1 on top. So my final answer is negative 2n over 3m cubed. Next one, we now have a negative exponent we're distributing in here. So the first thing I want to do is distribute that exponent into everything inside. Now, there's a more than one right way to approach this problem. Some people do it in a different order. This is just the order that I prefer. So I have negative 16 to the negative 2 power. I have m to the third to the negative 2, so that becomes m to the negative 6. And then n to the seventh to the negative 2 would be n to the negative 14. I'm realizing you can't see my pencil very well, so let me go ahead and do this in another color here. That was negative 16 to the negative 2. That was m to the negative 6 and n to the negative 14. And on bottom, because the parentheses cover the whole thing, we have to distribute that negative 2 as well. So 8 to the negative 2, m to the negative 10, and n to the positive 4. So anything that's negative is going to move. So I'm going to kind of cross things out as I move them. So this is a negative exponent, and it's not because the 16 is negative, it's because the exponent is negative that this has to move. So negative 16 to the positive 2 power. This is going to move up top. 8 now to the positive 2 power. M to the negative 6 is going to move to the bottom, become positive. N is going to move, become positive. M is going to move up, become positive. And this is positive, so it's going to stay on the bottom. And so I kind of cross those out as I go to make sure I've kept track of what I've moved and what I haven't. So 8 squared is 64. And then m to the 10th. And on bottom, negative 16 squared is, let's see, I think it's 216 or 256. 256, that's right. And a negative squared becomes a positive. And then I have m to the 6th. And n to the 14 and n to the 4 becomes n to the 18. And these cancel out. So I have 6 m's on bottom and 10 on top. So there's 4 left on top. And I can actually reduce these. 64 and 256 leaves me a 4 on the bottom. And I have m to the 4th over 4n to the 18. Oop, there we go, move that over. All right, next one. We have some distributing to do here on both of these, and then we can reorder things, kind of like we did in that first example. So I'm going to go ahead and distribute the exponent first. I have negative 3 to the negative 3 power. X to the 5th to the negative 3rd is negative 15, and y to the negative 3. And then I have 6 squared. X squared to the 2nd power is x to the 4th, and y to the 4th squared is y to the 8th. And everything that's negative is going to move to the denominator, or anything that has a negative exponent. So 6 squared is 36, x to the 4th, y to the 8th. Those all stay on top, and then these have to move to the bottom. So -3 to now the +3 power, x to the +15, and y to the +3. We have 3 y's that cancel, and that becomes 5 left on top. We have 4 x's that cancel, and that leaves 11 on bottom. And then I have -3 cubed is -27. And I have y to the 5th on top and x to the 11th on bottom. And 36 and 27 have a common factor of 9. So 27 divided by 9 is 3. 36 divided by 9 is 4. So my final answer is 4y to the 5th over 3x to the 11th, and this is negative. I can move the negative out front, be on top or bottom. It doesn't change what we have here. All right, let's move on to the next page. Oh, that's already done. Scientific notation. Now, scientific notation is something that you always learn in a math class, but honestly, the most places you use it is in science classes. So science teachers will expect math teachers to teach scientific notation, but we teach it and then you never practice it in math again, and then you forget it, and then you go to a science class and you've forgotten how to do it. So this video will hopefully be a good reference for you to come back to when you need to use scientific notation. So this is what scientific notation looks like. We have something times 10 to some power. That a value needs to be between 1 and 10, cannot equal 10, needs to be less than 10, and it can equal 1, so less than or equal to 1. A can be positive or negative. That's what these absolute value bars mean, is that as long as the absolute value of the number is between 1 and 10. And yeah, that's, all we're really doing. Our exponent here on the 10 is going to be either positive or negative, and depending on whether it's positive or negative will help us kind of decide whether we're moving our decimal to the right or left. So we want to turn these numbers that are in scientific notation into decimal form. So essentially what this means is we're multiplying this number by 10 7 times. Now, what we can do is, if we think about this, if I multiply this number times 10 7 times, I'm going to get a really big number. Every time I multiply by 10, my number is getting one more 0 bigger. So I'm going to move my decimal place 7 places to the right, and that will be this number. So 1, 2, 3, 4, 5, 6, 7. And all those empty spaces get filled in with zeros, so my answer is -6, 2, and then I have 1, 2, 3, 4, 5, 6 zeros. So that's this number written in decimal form. Now, if my exponent is negative, what that means is this is being divided by 10 3 times. So now my decimal is moving the other direction 3 times. So my answer is 0.002019. And this negative exponent doesn't make the number negative, it's still positive. So now we're going the other direction. Now I have these really small or really large numbers that I want to turn into scientific notation. So let's think back to what we were just doing. A really, really tiny decimal, I had a negative exponent. With a really, really large number, I had a positive exponent. So I already know when I multiply by 10 on these, this one's going to have a positive exponent, this one's going to have a negative exponent. And now we need to figure out how many places am I moving my decimal. So I want to try and get a number for my a value that is between 1 and 10. So I'm going to move this over until I get that. I'm moving it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's not quite enough because this is still less than 1. 0.802 is still less than 1, so let's move it over one more time. That would be 11 places, and I would have -8.02. And that's now in scientific notation. We can do the same thing with this one. My decimal's right here. I need to move it that way as many times until I get a number between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This number, I've now hit actual integers here besides 0, and this is still way too big, so I need to keep going. 11, 12. 34 is still bigger than 10. One more, 13 places. So my number, my A7, and my exponent here is going to be 13 because we moved to 13 places. All right, so now let's do some multiplication and division of numbers in scientific notation. This is actually just going to be using those exponent rules we were using on the previous page here. I have 6.1 times 10 to the 5th times 4 times 10 to the negative 9th. So 6.1 times 4 times 10 to the 5th times 10 to the negative 9th. Well, 6.1 times 4 is 24.4 times 10, and 5 and negative 9 becomes negative 4. We're adding those together. Now this looks like it's in scientific notation, but there's one problem. This number is not between 1 and 10. So here's a trick you can use. 24.4 is the same thing as 2.44 times 10. These two pieces here are the same. 10 times this gives me this. And bringing the rest of this down, times 10 to the negative 4th power. Well, now I can group these two, 10 to the 1st power and 10 to the negative 4th power. That gives me 10 to the negative 3rd power. We can do this similar thing with division. 1.8 divided by 3 is 0.6 times, and then this 10 to the negative 2, that can move up, 10 to the 2, and that becomes 10 to the 6th. And this looks like scientific notation, but it does have one problem with it. This is less than 1. So now instead I can borrow a 10 from here. 10 times 10 to the 5th is 10 to the 6th. So this is equivalent to this times 0.6. And then I can group these two together. 0.6 times 10 is 6 times 10 to the 5th. And now it's in scientific notation. All right, let's go ahead and move on from scientific notation. And actually, now we're going to be looking at rational exponents and radicals. Okay, so if I have a radical, this little part here, this n, whatever type of root it is called the index. And the number inside is called the radicand. And so here's some rules for square roots. Square root of something squared is the absolute value of that number. And then if we have products, we can separate those. Division can be separated as well. Like radicals have to have the exact same index and the same radicand. So same thing inside, same kind of root. Rationalizing the denominator means to get the square root out of the denominator, and these are the steps for doing that, and we'll see that in an example later on. We have other kinds of roots besides square roots. We have the nth root of a equals some number b. If n is even, a and b both have to be greater than or equal to 0. If n is odd, a and b can be any real numbers, so positive or negative. All right. Again, some more rules about types of roots and whether they have to go in absolute value or not. We'll see that in an example. And then again, for any kind of root, not just square roots, these same rules apply. Now, we can also talk about rational exponents. And what that means is an exponent that's a fraction. So the way we can kind of translate this is this kind of rule right here. If I have a to the power of m over n, m is the power, n is the root. So n is the index of the root and m is the power. That power can go inside the root or it can go outside after you've done the root. And then we can also use negative rational exponents. So let's practice some of these. We want to simplify all of these. So negative 125 to the 1/3 power, that's the same thing as the cube root of negative 125, which is negative 5. You can do cube roots of negative numbers, you just can't do square roots. So odd roots are okay, even roots of negative numbers are not okay. Here we have a negative exponent, so the first thing I'm going to do is move that to the bottom and become positive, and then I can rewrite that. and the top is the power, the bottom is the root. So 4th root of 16, and then I'm going to put the power on the outside. The 4th root of 16 is 2, so 2 cubed is 8. Here I have negative 8 to the 2/3, but be careful here, there's a difference. This negative, the way I would encourage you to rewrite this is -1 times 8 to the 2/3 power. That negative is not part of this. That exponent is applied first. So I have -1 times, and the top number again is the power, the bottom number is the root, so cube root of 8, and that whole thing will be squared. Cube root of 8 is 2, and then 2 squared is 4. The next problem, again, you really want to be careful here. This negative is not part of that. We have to evaluate this first and then multiply by the negative, just like I did here. So again, it might be helpful to multiply or to rewrite this as like that. And so again, now we have a negative exponent. It can be moved to the bottom. So instead of just 1 on top, now I have that -1 on top. And I have 81 to the 3/4 power. And that's a root of 4. And then to the 3rd power. 4th root of 81 is 3. 3 cubed is 27. Now we can look at problems that have multiple variables and multiple things going on here. First off, in this first example, I have all my bases are the same. All of them are y's. So y to the 7/5, y to the 4/5, those get added together. So 7 plus 4 is 11. And on bottom I have y to the 1/5. And remember, we subtract these. So y to the 11/5 minus 1/5 gives me y to the 10/5, and 10 divided by 5 is 2. In this next example, we need to distribute those exponents before I do anything. So 3 to the 4th power is 81. X to the 1/2 to the 4th power would be x squared. On bottom, y to the 3/8 times 4 would then be 12/8, which would reduce to 3/2. And then here I have y to the 1/2, which becomes y to the 3/2. And then here I have 3 cubed, which is 27. And x to the 4/3 to the 3rd power just becomes x to the 4th. So there's some reducing I can do here. 81 divided by 27 is 3. And I have a y to the 3/2 and a y to the 3/2. Those cancel out. And then I have x squared and x to the 4th. 2 of those x's cancel out, and I'm left with 2 on the bottom. So I have 3 on top and x squared on bottom. That's it. So this ugly thing turned into actually a pretty simple answer. All right, this next problem, we have these radicals here, and we want to try and pull out as much as we possibly can. We don't have to turn these into rational exponents or anything. We can just try to simplify things as much as possible. So 96 is the same thing as 48 times 2. I'm going to show you kind of a tool you can use here. We can use factor trees. 96 is 2 times 48, 2 is prime. 48 is 2 times 24, 2 is prime. 2 times 12, 2 is prime. 2 times 6, 2 is prime. 2 times 3, and those are both prime. So when I'm thinking about what I can pull out of here, I need 4 copies of something to be able to pull it out of this root. So I have 1, 2, 3, 4, and then I have an extra 2. So I can pull a 2, 4th root. And as far as numbers are left, 2 times 3 is 6. And then I have 14 p's and 7 q's. So I'm actually going to write all of those out. It might seem silly, but you'll understand why in just a minute. 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14. and then 7 q's, 1, oops, 2, now again, I need 4 copies of something to be able to pull it out. So I have one set of 4, another set of 4, another set of 4, and then there's some left over. And then for q's, I have one set of 4, and then there's 3 left over. So when I'm simplifying that piece here, I now have 1, 2, 3 p's I can pull out, and 1 q I can pull out. So out front, I now have 2 p cubed q, 4th root of, and then I have 2 p's and 3 q's. So p squared q, oh, I forgot the 6. Now for this one, I can do the same kind of thing, but for the sake of time here, I'm going to just go straight to it. I don't have anything I can pull out here. I have 27 inside, and then I have 1 p that can be pulled out, and 1 q, and there will be 1 p left over and no q's left over. So I can go ahead and combine things now. Everything underneath the radical can go together, and everything out front can go together. So I have 2, I have 1 p and 3 p's is 4 p's, and then q and another q is q squared. And then 6 and 27, 6 is 2 times 3, and then 27 is 3 times 3 times 3. So I actually have 4 3's. So I'm going to just, for running out of space sake, pulling out another 3. 3 times 2 will be 6 out front. And then I just am left with that 2 inside. And then I have 1 p plus 2 p's will be 3 p's. And then q to the 3rd. And that's as simplified as we can get this one. I just realized some of that was out of the screen, so hopefully you can see it now. All right, this next one we're going to go ahead and go through really quickly, but I'm seeing that this video is getting really long, so I'm going to try and do it pretty fast. These are both cube roots, so we can go ahead and put this all underneath one fraction. 5x to the 5th y and 625x squared y to the 4th. Let's go ahead and simplify this. 5 and 625, this is going to turn into 125. X squared cancels, and I have 3 on top. And 1y cancels, and I have 3 left on bottom. So I have the cube root of x cubed over 125y cubed. And these are all perfect cubes, so I can cube root each of them. The cube root of x cubed is x. The cube root of 125 is 5, and the cube root of y cubed is y. And I'm going to go ahead and stop this video here, and then we will pick up with rationalizing the denominator in part 3.